purpose of this project is to filter the stock price of a company, which tends to be sporadic. Once high-frequency content is removed, the curve should look smooth while maintaining its original shape. One of the simplest ways to do this is through an averaging filter. It's a low-pass filter. Here we tried an averaging filter with 2 samples and with 3 samples. Notice that it's pretty similar to the original raw data, and you can't see any real difference until you zoom in really closely, in this case to a full month. The problem with averaging 50 samples altogether is that you can't make it causal. So your predictions end up being way after what you want to predict. We're actually not going to address this issue, but there are other issues with averaging filters that we're going to address. One of the problems that we'll actually address is the side lobes. Notice from the graph that all 3 of these averaging filters actually let through some of the high-frequency content that we were trying to get rid of in the first place. Now, the 50-sample averaging filter does a much better job of reducing the side lobes, but it also doesn't let us choose a cutoff frequency as neatly. If we want to perfectly get rid of all of the side lobes and be able to choose our cutoff frequency perfectly, then we have to use a rectangle function that's defined in the red box, that it passes all of the information below a cutoff frequency, omega sub c, and it rejects all of the information above that cutoff frequency. If you do an inverse discrete time Fourier transform on this frequency response, then you actually end up with a sinc function. I tried out the sinc function, and at first it looks like it's consistently under-predicting what it should be saying. This is terrible. This is a disaster. I thought the sincs were supposed to be perfect, just eliminating the high-frequency content. Well, it's actually doing what I told it to. A sinc is infinitely bounded, so to compute a perfect sinc, I would have to go through and compute an infinite number of possibilities for every single point, and I just don't have that kind of time. So instead, I cut off the side lobes of the sinc, and I just compute, in this case, the first 5 non-zero sinc values. But you can think of that like a weighted average. In this case, I am trying to get a total with only 92.44% of the weighted average. So to compensate, I have to put that 8% back in. Notice that when we add the compensation back into the filter, we actually get very close to what the original raw data values were. We get so close, in fact, that it's hard to tell a difference unless you zoom in pretty closely. The reason for this is that we chose our cutoff frequency at 0.5 pi. That's a full sinusoid every 4 samples, which is pretty fast. If you're looking at a plot of a full year, you're probably not going to see very much change. But here, zoomed into a month, you can tell the difference. To get smoothing that's noticeable on a wider time frame, all we have to do is eliminate some lower frequencies. So I chose a cutoff frequency this time at 0.1 pi. Now you'll notice that the smoothing is noticeable on the order of a year instead of a month.
In addition, now since our filter only requires 5 samples, making it causal isn't so much of a problem. It only delays input by 2 samples. This is far more realistic for real-time computation than the 50-sample averaging filter.